Hello students, welcome to series of lectures on digital speech processing. So in this video you'll be able to learn the classroom discussion topic on linear predictive coding and the basic principles of LPC. So let's get started. So on completion of this lecture and you'll be able to analyze the speech parameters using linear predictive analysis. Right. So these LPC methods are the most widely used in speech coding, speech synthesis, speech recognition, speaker recognition, and verification for the speech storage. Okay. And for instance, if you take any kind of the voice signal that you are going to be recording, okay, so you have said something and you have recorded and you have stored it. So there is a lot of process which are involved, right? But when it comes to the LPC methods, okay, so the way how we are going to be storing the speech signal that you have already recorded, and not only that, using LPC method we can also distinguish who is the speaker he is speaking, whether the male speaker or the female speaker, because as per the frequency ranges of that, for male when you consider, the frequency will be lower when it comes to the women and then children. Okay. And also speech recognition, speaker recognition, the identification of a speaker also can be done with the help of the LPC, and also speech recognition. So what the speaker is speaking, that can also be identifies with the help of the linear predictive coding. Right. So in what way we need to estimate the parameters? Okay, that is a basic principle that we can see. So LPC methods which provide extremely accurate estimates of the speech parameters and does it extremely efficient manner. Okay, that is the greatest advantage that we can see with respect to the LPC method. So the basic idea, what is the basic idea of the linear prediction is that the current speech sample can be closely approximated as a linear combination of the past samples. Okay, for instance, so let me draw here. So this is a kind of the speech signal that you have recorded on a time basis. This is the way, and when you take the samples, like this is the first sample, this is the second sample, this is another sample, this is another sample. So I would like to estimate this sample, for instance. So this is my current sample. Okay, so with the help of the LPC, how we are going to be estimating the current sample? By taking the knowledge of the past samples. So these are the past samples, past sample, past sample. This is also one past sample. Okay, this is the immediate past sample, for instance. Okay, so what we are doing here is that with the help of LPC method, or the LPC method will do like this. If you want to estimate the current sample, this is my estimation of the current sample. How we are estimating? By taking the previous samples data. Okay, the previous samples data are very important for us to estimate the current sample. And after estimating this, for example, this is my current sample now after a period of time. Okay, so how we are going to be estimating? Taking the previous samples. Okay, so all the previous samples from here to here that we are taking. So that is the way we have represented in the mathematical form. The speech signal S of n is equals to summation k equal to 1 to p alpha k. So this alpha k is very important for us to estimate the current sample. Okay, so this alpha k into S of n minus k, the delayed version of the k. So this alpha k nothing but the prediction coefficient. So how we are going to be predicting? Okay, this is the way how we are going to be predicting the current sample with the help of the previous samples. Okay, so this formula or the mathematical expression is very important for us to estimate. Now, so for periodic signals with period np, it is obvious that S of n equal to S of n minus np we can take, but that is not what LP is doing actually. It is estimating the S of n from the p values, the pth order actually. This is an order of the period. Okay, so the most recent values of S of n by linearly predicting its value. Okay, so we are going to be predicting linear. In what way we are naming this is a linear prediction? For example, there is a straight line. Okay, So this is the sample 1, sample 2, sample 3, and for example the sample 4. So how the sample 4 can be estimated with the knowledge of the previous sample, and how the previous samples are located in linear position. So that way we are calling this the linear predictive coding method. So for LP, the predictor coefficient alpha k, which are determined or computed by minimizing the sum of square differences between the actual speech sample and the linearly predicted ones. So the normal speech sample, also we can write the mathematical expression that we have already seen in the previous slide. It just similar to that, but in place of in place of alpha, we are considering this is AK. This is the actual coefficient of a speech signal into S of n minus k. So this is the actual coefficient. So whatever the prediction coefficient that we need to consider, that has to be equated to AK. Then only we can say that the prediction coefficient is exactly matched with the actual coefficient, so that there will be no error signal. Okay, so the estimated speed signal is exactly equal to this actual speed signal. So that is our duty. Okay, so by seeing, you may be thinking it is very easy for us, but while doing analysis purpose, by doing analysis of each and every parameter, how we are going to be equating that alpha k. So in what way that alpha k will be equating to exactly actual coefficient AK. So that is a very biggest task for us. Now, so LP is based on the speech production and the synthesis models that you can also know, because the output of a speech is a linear time varying system, and which is exerted by either quasi-periodic pulses or the noise pulses. So this is the complete model of speech production model. In the previous slide also, in the previous video also, we clearly mentioned about this. The same thing when it comes to the Z transform domain, where h of z is equals to g of z into v of z into r of z. What is g of z? It is the glottal. What is v of z? It is the vocal tract. What is r of z? It is the radiation of the lip, the way how we are pronouncing the sentences. Okay, the complete I'm calling as the h of z. So when it comes to the estimating the prediction coefficient or estimating the current sample of a speech signal, so there are so many varieties of the methods which are there. Okay, so one of the LPC method that we are going to be using as a covariance method, most widely used, and also autocorrelation method. But as far as your syllabus is concerned, only two methods will be having. The other methods which are not there in your syllabus. Okay, we can also estimate the current sample of the speech with the help of the lattice method, inverse filter, spectral estimation, maximum likelihood, and then inner product method. But as per the syllabus, we will be having only covariance method and then autocorrelation method. So in our next series of the lectures, we are able to see what is the covariance method and then autocorrelation, and how the solutions to the prediction coefficients also we can see. So this is a basic principle of LP. I clearly mentioned the way how we are going to be looking for h of z. Okay, so when you want to apply into the z domain, you'll be getting like this: h of z equal to 1 upon 1 minus sigma ak into z power minus a. So this is the standard transfer function of the system. So the basic equations I clearly mentioned. Normally when you want to design any kind of the filter, so obviously because we are going to be estimating the current sample and there is a possibility of the error. But how we can define the error? Error is nothing but actual speech minus the prediction. Okay, so S of n minus prediction. S of n minus summation k equal to 1 to p alpha k S of n minus k. Okay, what is our job? We need to reduce this error signal. So in what way we need to reduce? For example, error signal E of n equal to 0. That is our job. So to do that, what we are doing? We are exactly estimating. We are estimating this. The whole function will be equating to S of n. If this is S of n, and we will be getting error equal to 0. Okay. So there is a procedure. So the prediction error is the output of a system with the transfer function. So if the speech signal obeys the prediction model exactly, then we can call alpha k equal to AK, that we clearly seen in the previous slide. Now there are some of the issues which are there for the estimating the linear prediction. So first we need to determine the alpha k directly from the speech. and we need to estimate alpha k from the short segments of the speech. Short segment nothing but we want to apply the windowing methods, and resulting alpha k assumed to be the actual AK in the speech production model. Thank you students. Thank you for watching this video.